Hi there, we're in the Salmon River Canyon and we're going to talk about sediments. So right here in my hand, I have some sand that comes from this beach that I'm standing on right here. This is actually a landform known as a point bar. And point bars form along rivers where the current swings away to one side of the canyon and leaves a low energy zone on the other side. And where the energy is not as big or not as strong, we see particles like sand fall out of suspension. That is, they're being held in the water, being moved downstream, but where the energy gets a little lower, the physics of the water can't hold them up anymore, and they actually fall out and become deposits of large bodies of sand like this that look like beaches. So in a river system, the highest energy part is out where the water is moving the fastest in the deepest part of the channel. And that's also where we see the largest particles, the largest clasts, or the largest sediments being moved in a river system or sometimes being deposited there. So in the bottom of the river channel, we actually have larger rocks, and these can be from pebble to cobble to boulder-sized rocks that are down in the bottom of the channel. As we move this way, away from the highest energy part of the river, the power that a river has to move sediments gets reduced, greater and greater distance away from the central part. And as a result, the particles get smaller and smaller and smaller. So as we are here on the edge of the channel, outside of its highest energy zone, we're in a spot where apparently the water lacked the ability to transport sand-sized particles. So as a result, they fall out of suspension and they become deposited in big areas like this, like a sandy beach. Farther away from the channel, you get finer and finer and finer sediments. So you get your silts and your clays can be deposited other places where the water is very, very gentle and doesn't move very much. So outside of the area where water is moving, we can get other kinds of sediments being created, being transported, being deposited. So up on the flanks of the canyon where the land gets very steep, gravity plays a very important role. So as rocks physically weather, fall off of the banks, fall off of cliffs, they can roll down, they can become deposited within low points in landscape like little side canyons, little gulches at the base of cliffs. They can build up and make piles, and then eventually they get steep enough they can move again and move again. Eventually all the rocks will sort of work their way back down to the river in time, where they can become rounded by the river's moving action. They can become entrained, that is picked up and moved, transported and deposited elsewhere. So the whole cycle of production of sediments, their transport, their movement somewhere else, and then their deposition happens over and over and over again, even within small sections of a canyon or any other kind of landscape. So here's an example of an angular cobble-sized rock. This rock probably fell off of one of the banks or the cliffs next to the Salmon River and has just been rolling down, working its way down, down, down closer to the river. In time, it'll go into the river itself. The river will roll it around, smash it against other rocks. It'll start to wear these points off, become more smooth and more spherical through time. So rocks that are formed by physical weathering, chemical weathering, that fall off or influenced by gravity, typically are pretty angular. So they'll have very sharp edges on them, kind of blocky, pointed shapes. And eventually, as they work their way down, become more and more weathered, they can start to get rounded off on their edges and points. By the time they get into a river system, they will tumble, roll, hit other rocks, and they start to get shaped into spheres. So typically, when you're looking at sediments, you can tell if it came from what's called a short distance transport zone. Did it fall off a cliff and roll a short distance? If so, it'll look pretty angular. Did it spend some considerable time in moving water, being ground up and rounded off? Then it'll have a rounded to sub-rounded shape. So the shape of the clast also is pretty important. You need to look at that. So we're about 30 feet above the channel of the Salmon River, and here there's a deposit of rounded cobbles. So when we think about what the environment of a river is like, the energy required to move rocks of this size or sediments of this size is much greater than other parts of the river. So this is probably being deposited at a time when the river was higher in its vertical position, as the channel was up here 30 feet higher than it is now. and also is in a part of the river system, and if you think of its cross section in the different depositional environments of a river, it was the part that had more of the higher energy. So this is on the edge of the channel or right in the bottom of the channel perhaps, and it's pushing a lot of this heavier material in sort of the channel load. When we look at the sediments that are associated with this deposit, we can see that they have a particular shape. Mostly they're rounded, and they're pretty smoothed off, but they began as large blocks of bedrock, and they broke down, were worked through the river system, and became rounded off, transported from someplace upriver. These don't match the geology of the canyon around us right here, and they came to rest here though at some point in the past. So by looking at deposits like this, we can actually map out sort of where the position of the channel has been through time, or we can basically talk about that this deposit was created very likely by moving water of a certain energy, power, a part of that river system, just by looking at the sediments alone, because we know how the sediments go along with certain kinds of depositional environments. So we're here in the Salmon River Canyon in western Idaho, and behind me is a big geologic profile that shows examples of lots of kinds of sediments. Sediments can be anything that breaks down into particles from, let's say, bedrock. It could be organic matter breaking down into smaller pieces. Basically, sediments are particles that get created by natural, sometimes even cultural processes that are small bits of things that get eroded, transported, deposited, sometimes changed in place. But the point is that sediments come in all shapes and sizes, and learning how to describe how these sediments are in a profile, let's say, how they appear, what their distribution is, how are they related to other sized particles, can tell us a lot about how a certain kind of deposit was formed. So in this profile behind me, we have examples of sediments that come in a wide range of sizes. The largest ones we would call boulders, and the smallest particles we would find in this profile would probably be clay-sized. Very, very teeny-weeny ones. You can't even see them with the naked eye. They're so small. So what's remarkable about this profile is that it shows lots of different particles together. So we can also talk about the concept of sorting. So when we look at a stratigraphic profile, any particular deposit might have particles of a very specific size. Sometimes there's a range of sizes. Sometimes that range is enormous. Like the one behind me. This one has a very large distribution of grain sizes. In fact, we would probably describe this profile as extremely poorly sorted. Some natural processes like the movement of wind, water, gravity, glaciers have certain capabilities in their application of force. So in some cases, like with wind, there's a really narrow band of energy that wind will exert on the Earth's surface and has this sort of limited ability to move sediments of only very smaller sizes. Water, on the other hand, depending on how much water is flowing through a channel, let's say, has the ability to do larger amounts of work than wind. And in fact, it can move much larger particles than wind. Water also can move small particles if the amount of force or the amount of power within a moving column of water, for example, is very low. Very small particles can only come out of movement, or what's called transport or suspension, let's say in a column of water like a river. They can only come out and come to rest on a surface if the water has almost no energy. So that we would have something like a still body of water, like a lake or a pond. In the case of a lake or a pond, when there isn't a lot of wind movement of the surface or there isn't big currents going into the lake, that water body can be very, very quiet and gentle and have no energy really to move particles around much. So the very, very finest materials can settle out and come to rest on the bottom of a body of water in a lake or a pond. Also, in very deep portions of the ocean, you can have very fine particles coming out, blanketing the bottom of the seafloor. So in this profile behind me, we have a great example of a particular kind of geomorphic action that you sometimes see in landscapes where you have very high relief. That is, you have parts of the landscape that are very high in elevation above other parts. The deposit behind me is probably created by a landslide. And one of the ways that we can tell is that there are very large boulders set within very fine sediments that also contain a wide range of other particles. To get something like this deposited by, let's say, wind, well, I wouldn't want to live on the planet where that happens. That would be so much wind, it probably wouldn't be any biological life on the surface. If these deposits were created by water, we would expect to see a lot more size sorting. You might get situations where finer materials and coarser materials are sort of deposited in different layers, or we might see a lot more roundedness to the clasts. As it is now, these are very angular. And they're very angular because they came down in very violent force by gravity, moving, tumbling, crashing down to the bottom of this canyon, coming to rest right behind me on this landform. We also can trace out the extent of this kind of deposit up and down the canyon and relate it back to a very obvious place in the landscape where it looks like a block of the wall, the canyon, actually came down. As we study stratigraphic profiles, we pay attention to what kinds of sediments are here, their sizes, their shape, their distribution, their sorting. Are they bounded below and above by very hard boundaries, lines of contrast that show one sediment below and another different type above it? And what is the shape of that, and how can we trace that out in the landscape? These are all clues for us to understand the layering of how deposits accumulate in a landscape and what they might tell us about the environment in which people of the past made their living. So we've talked a little bit about sediments that are created by wind, by water, by gravity, and even glaciers. There's another kind of sediment that's created by a process that's a little unique, and these are what are called pyroclastic sediments. Pyroclastic sediments are particles that are created from the eruption of volcanoes. And this white layer right next to me is just such a kind of sediment. It's a pyroclastic deposit. In this case, we're looking at sediments that were created during the eruption of Mount Mazama, which, as everybody knows, is Crater Lake. This sediment was created as Crater Lake erupted about 7,000 years ago or so, and blew its top. And in the process of it erupting, the froth of lava that was inside the caldera created small bubbles that cooled as glass and then shattered and blew apart into really small particles that went up in the air, traveled the direction of the wind, and then laid down. They fell out of the sky, sort of the particles would come out of the sky and drape the landscape. In the Salmon River Canyon here in western Idaho, a lot of these sediments would come and coat the landscape. Later on, gravity, wind, water would push them down deeper into the canyon. So as these particles came to rest on the canyon, they would get washed together, slide with gravity, get overall worked down and more concentrated into thicker deposits. So this layer right here isn't just the thickness that would have happened after the airfall event. That is, the eruption goes in the sky and then it falls out, rains out, sort of and drapes landscapes. This is a little bit too thick for that. And it also includes small rocks and pebbles and things, which are indicators that it isn't just something that fell out of the sky. It got redeposited later at a lower elevation in this canyon. Pyroclastic sediments like these can be valuable as time markers because they are tied to a known eruption that can be radiocarbon dated, or there's other dating techniques we can figure out when that eruption happened. Whenever you see a deposit like this, it can be a clue that the landform is somewhere close to that time. Now, there's a caveat to this rule because, as I mentioned before, these things can get redeposited. In fact, they can get redeposited many times in a landscape. So you often cannot be entirely certain that a deposit like this dates to exactly the age of the eruption. Pyroclastic sediments that are in the grain size of silt into very fine sand are typically referred to as tephra. So generally it's incorrect to call them ash because they're not really from the combustion of carbon material like wood ash. But we tend to often hear this or see it written. But tephra is the correct term. And these particles are so small, when they get blasted in the air from an eruption, the winds can take them aloft and they can travel long distances. So tephra is largely very small glass particles, that is silica plates that have other elements in them that can be used to figure out what volcano they came from. But largely we're looking at a big deposit of silica. As you can see to my right, we have some stratigraphy, that is layering of geologic units that form through time. And this deposit, this lighter sandy deposit, and this darker, still sandy but has a little bit more silt, both of these deposits have archaeological materials in them. Now the question that the geoarchaeologist tries to solve is, why do these look different? Where did they come from in terms of different parts of the landscape? And also, what is the mechanism for building up this deposit? So we can look at the fine sediments themselves, we can subject them to laboratory analyses and figure out what they're made out of, what's their sizes, shapes, composition, mineralogically. And we can do that for both of these. But then what we have to consider is that not only is there a natural process of deposition, the addition of material to the site, because it's an archaeological site, we should expect that there are cultural modes of deposition also. So here we can see a larger rock embedded into the wall here. And throughout this brown deposit, we see other larger rocks and thousands upon thousands of artifacts. So we know that there are two sources of deposition that create the site. So in front of me, what we have is an arrangement of objects sort of sticking out from a dirt bank. And this is a great opportunity for us to study a very simple aspect of stratigraphy. So when I approach a profile like this and I want to understand what is it that's in front of me and how can I use this information to interpret what happened here at the site, I get back to basics. I want to talk about the things that are like each other, things that are different from each other, those things that look like they're continuous, those things that look like they're breaking up lines, and so on. So at one level, the study of stratigraphy is basically an exercise in recording what's right in front of you. And it can be somewhat artistic, trying to capture information about layers, the color, the texture, the shape, and so on. And so don't discount all your artistic abilities, because actually they are kind of important. Sometimes we do this work off of photography, but it's also important to be able to do this live in the field and based on what's in front of you. So I'm putting my hand here on top of the surface that is the modern surface. A few weeks ago, there were live plants growing out of this. We came in, knocked them down so we could start our work. So you could say from a stratigraphic perspective, this is the most recent surface. This is the modern surface. Below this, we are going backwards in time. As we go deeper, 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 we get older and older and older in time. Now there are some exceptions to this. When you have situations where there are geologic units or stratigraphic units that are intrusive into, that is cut into older deposits, you can get younger material deeper than older material in a sense. So right here you can already see an example of this. We have some black visqueen plastic like you might use to put over to keep something dry. In fact, we use it here at the site to cover it in case we get rain. We've got some tin cans. We have another kind of can here that's a beverage container. If I move over this way, we have plastic 6-pack holders. Now, these are all common things we all know about. So we can actually relate some of these objects we see here to time by looking at what the objects are. So sometimes in stratigraphy, we actually can look at the objects and they give us some ideas about how much time has elapsed since these things were actually put in the ground somehow. So one of the clues is we can look at the technology of the containers in this case. So this beer can right here has sort of a triangular hole that opens at the end, and it actually is opened by this thing right in front of me. This is called a pull tab. And so what you would do is this pull tab would be in the hole, you would grab it and tear it open. But the problem with these things is they commonly will get thrown on the ground. If you're walking around with bare feet, you could step on them, they would cut you. So by the early 1970s, these went out of use and they stopped making them. So we can already guess that we're at least looking at a stratigraphic unit that contains these objects that dates to probably not much later than the early 1970s. It could date earlier, it could date in the 60s. There were different technologies in the 50s, but these were pretty common in the 60s and 70s. Plastics were also pretty common in the 60s and 70s and before, but that doesn't necessarily help us out. But there's one key piece of information that actually narrows this down. And as the students were excavating this, they found a copper US Lincoln penny from 1972. So combine it with this technology that went out of use in the early 1970s, a 1972 penny, we're probably looking at objects that were laid down in the early 1970s, probably 1972. Not necessarily earlier than that, I think, because they weren't making 1972 pennies in 1964, right? That makes sense. So as we look in the wall, we can see some differences in color. I think everyone can probably agree that we're looking at some layers here that are lighter colored and they're sort of horizontal. There's some darker ones. And we also can see a darker line that goes down, 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 cuts across like this, and then comes back up again. So this is, at least in 2 dimensions, what's called a negative space or an accommodation space, or to put it more simply, someone dug a hole. So someone dug a hole and they probably put this stuff in there. So if we think about our own life experiences, when you're out, let's say having a picnic or a party or you're camping, what do you do with your trash? Well, sometimes there's not really anything to do with the trash. So to some people's minds, the responsible thing to do is let's dig a hole and bury it. Well, I'm actually grateful for this because it gives us a great opportunity to learn about stratigraphy. We can talk about the layers, that there's a pit feature here, that it's full of these objects that relate to a very specific time period. These are all essential aspects of understanding how to interpret an archaeological site. Now, from the 1970s, as we go deeper and deeper, we start to get into older and older deposits. And we know from the excavations that are happening here right now with the field school that the surface that I'm standing on is about 8,000 years ago. So it actually dates to about 8,000 years old. Now, so how did we go then from 8,000 years to 1970 in such a short distance? Well, one of the ways we can do that is, as I mentioned before, you can get people to dig a hole that intrudes into older deposits. But another thing that's important about this place is that the top part of the site was actually cut off during road construction in the 1930s. So it used to go thousands and thousands of years of layers of time above me, but that all got cut off in the 1930s. So we've lost a lot of time here due to what you might think of as erosion, but it's basically due to road construction. So bulldozers pushed it into the river so they could create the road that's actually behind you. So if I were trying to describe this profile, I would probably get a piece of graph paper and I would start by measuring out the section I'm going to work on. How long is it? How deep is it? And I would use the graph paper to establish a scale and then begin to draw in all the lines that I can see. You know, which ones are the same, which ones are different. Do I have objects sticking out of the wall? I would draw all those in to try to get sort of a reproduction on a page of paper, the thing that I'm seeing in front of me. And I want to try to account for everything that I can see. Nowadays we use digital photography as well. We can take a digital photo. We can then draw lines in software programs that allow us to do illustration on photos, and it makes it a little bit faster. Either way you do it, it ends up being sort of the same. It's a representation of a geologic profile, and you're making an interpretation. So if I draw a line that sort of encompasses all this material, this junk inside sort of a U-shaped deposit, I'm making an interpretation that there probably is something maybe like a pit. Or it could even have been a ditch that someone threw stuff into, but then it got